Hi everyone, welcome to my YouTube channel, City of Electrons. And in this video, we are going to talk about this. What's that? Now check this out. In order to filter off signals we don't want and get only signals we need, and only signals we want, we need to do something to the original signal to get our desired output. The thing is, what you receive a signal, what you need is the message from the signal. Now, any other thing attached to it, maybe electrostatic noise or maybe some other thing, other signal attached to it, you do not need those ones. Okay, you do not need those ones. What you need is the message in the signal, in the signal you get. So, how to get just the message? We need to filter off maybe some frequencies we don't need, maybe the higher frequency or the lower frequency. We need to filter off some parts. We can reshape signals to what we want. Are we getting it? We can reshape signals to what we want. Okay? Of course, a signal is a function of time that carries message. Okay? A function of time that carries message. So, waves like this, they just represent signals. Okay? They just represent signals. So, of course, this is a sinusoidal wave. Okay, so there are different waves, there are different waveforms. Okay, so let me just write some of them. Okay, so these are important waveforms: sinusoidal, step, pulse, square, ramp, and exponential. Don't worry, you don't need to memorize them. As we work with them, some of them here, you will get used you get used to them. Okay. So note that out of these 6, this particular one, sinusoidal waveform, it preserves its shape when transmitted through a linear network. Okay, now what am I talking about when I say linear network? So a linear network is a network that contains linear elements. Linear elements in the sense that the elements the linear elements, they are elements whose input is proportional to their outputs. Whose input is proportional to their what? Outputs. So for this guy, for sinusoids, if it goes through a linear network, it preserves its shape. Okay? For any other one, any other waveform, of course, every other waveform, they are non-sinusoidal. So any other waveform, when they go through a linear network, their shape is changed. They are reshaped. Okay? So that means we can say non-sinusoidal waveform, they are reshaped when they go through a linear network. Okay? When we say wave shaping, it just simply means modifying a signal shape using a circuit. So the circuit used is the wave shaping circuit. And now we just talked about the fact that sinusoids, so when they go through a linear circuit, they remain the same, they maintain their shape. So, but the process whereby the form of a non-sinusoidal signal is altered by transmission through a linear network is called linear wave shaping. But if the process whereby the forms of the signal is changed by transmission through a non-linear network, for that you say is what? Non-linear wave shaping. Okay? So, yeah. Okay, so for the linear element that makes up the linear circuit, of course, that's for mainly resistors and capacitors. Okay, so you see linear networks, they are RC circuit, resistors and capacitors. Then for non-linear network, they include diodes and transistors, inductors also, inductors. So the thing is, Of course, inside this, in the non-linear network, you can have linear elements also. You can have linear elements also, resistors and capacitors. But the thing is, once you have non-linear elements in a network, that makes the network non-linear network. Okay, so yep. So just like we said that for linear network, the input is directly proportional to the output. So by increasing the input, you increase the output is also increased. But that's not true for a non-linear. Okay, by increasing the input, it doesn't mean that the output is increased. Okay, for diodes and transistors and inductors. Now, if you reverse the polarities for resistors, it will still behave like it will still exhibit the same behavior. Same for capacitors, but for diodes, that's not true. Okay, and transistors, transistors are built with diodes. Okay, so yeah, there is an effect when you reverse polarities for these guys, but not so for capacitors. So now let's talk about the kind of waveform that goes through the network which can be reshaped. We just said that if a sinusoidal waveform go through a linear network, it will not be reshaped, it will maintain its shape. So for those that will not maintain their shape, those are the non-sinusoidal waveform. And for that we have the step waveform. Okay, so for a step waveform is one which maintains the value 0 for all times t less than 0 and maintains the value v for all times t greater than 0. This is what we mean. So this is for v, okay, voltage, and this is for time. Okay, so when time is less than 0, what will be the value of vi? Vi will be 0 for time less than 0, because you see that this side is 0. But once we get to greater than 0, we'll have values. Maybe this can be 10 volts, 5 volts, 1 volt, whichever, but something which is v. We'll have v once we have t greater than 0. That's for step function. Then for pulse function or pulse waveform, the pulse waveform amplitude is v and the pulse duration is tp. Okay, now what does that mean? Of course, voltage and time again. Now when t is 0, we have the value v, which can be 10 volts, 300 volts, okay, whatever volts. But when we get to tp, like at some certain points in time, this voltage will drop. Are we together? That voltage will do what? Will drop. So vi, which is this, equals v for 0 less than t and t less than tp. So from all this part, okay, so for this range, vi, which is the voltage, is equals to some volts, which is v whatever, 300 volts, whatever. Okay, then once we exceed this tp, the voltage becomes 0. Otherwise vi, which is voltage, equals 0. Okay, then for square wave, it's almost like this that impulse, but you will see it like this. A waveform is a waveform in which maintains itself at constant level v1 for time t1 and other constant level v11 for time t2. So for time t2, which is repetitive with a period of t equals t1 plus t2, and it's called a square wave. Look at what we mean here. Now, of course, voltage and then time. So look at this line. Okay, this is the center line, like the at this line v is 0, just like as we have this part. At this line v is 0 at this line. So v may be 20 here, 10, 5, 0. So at this line v is 0. That's the same line we have here. V is 0 at this line. So v is one value here, v is another value here, different values like that. But at this line, v is 0. So from this point to this point, the time changes. The time is 0 here. So the value of time, this is t1 from here to here. Here will be t2. If we extend this thing here, from here to here will be what? t3. From here to here will be t4, and so on. Okay? And so on. So yeah, from this point t1 to t2, that is your capital T, or that is your T, sorry, that's your T. Okay, because this is 1, 2. This we can say is a complete square, because if you put this together, as we drag this one back, you get a complete square. So this is just one part of the square and then complete square. So you have to sum up t1 and t2 to give you what t is. Okay, that's one period. Yeah, one period. Okay, so that's how square wave is. Okay, so 1 for 1 we got t1, then at this point we got t2. So just I know it may sound somehow, but just manage and go through with it. Okay, this is the last one for this video, quite short. So ramp, a waveform which is 0 for t less than 0, which increases linearly with t greater than, with time t greater than 0. So voltage and time, so it increases linearly. So you see it as a straight line. Okay, as vi is proportional to, directly proportional to t, and that's a constant there. Okay, so yeah, these are the waveforms in which are reshaped when they go through a linear network. Okay, so I'll stop here in this video. I'll stop here for now. So of course, like, share, subscribe, comment, and then I'll see you in the next video. Thanks for watching, and bye for now.